Today we're going to talk about how to do empirical formula problems. So the first part of that is understanding what an empirical formula is. Here in our notes, it says it gives the lowest whole number ratio of the atoms in a compound. So sometimes the actual formula for a compound could essentially be reduced to a lower whole number ratio of the atoms, and that would be the empirical formula. So for example, if we were talking about the compound C2H2 or C6H6, those are actual legitimate molecular compounds for which you would say the empirical formula for both of those is CH. So it's just like sugar or glucose, C6H12O6, that's the formula for sugar. But if we wanted to know sugar's empirical formula, it would be CH2O, because that shows the ratio of atoms of carbon to atoms of hydrogen to atoms of oxygen. Okay, so why do we care? Well, you can use elemental analysis data of an unknown compound. Sometimes that's given to you as percent composition. Sometimes it's given to you as actual masses. And you can determine the empirical formula of a compound to help identify what the unknown compound is. So that's what we're going to practice. So a couple more things about empirical formulas. Remember, any chemical formula gives you the ratio of atoms in the compound. And the ratio of atoms is equal to the ratio of moles of atoms or dozens of atoms. So for example, the ratio in aluminum chloride, you got 1 aluminum, 3 chlorines. So you have a ratio 1 to 3 there. Also in moles, so you could say it's 1 mole to 3 moles. Well, you could, in theory, have this aluminum, and then you have a 0.5 down here, and chlorine 1.3. Notice this also shows the same ratio. It shows a ratio of 1 to 3. But we aren't allowed to use these kinds of numbers when we write the formula for something. We can only use whole numbers in chemical formulas. So when we do these problems, we're going to get some decimals like this, but which we've essentially found the ratio, but we can't leave them like that. So we're going to have to do some math to allow us to convert them to whole numbers. All right. So this is the basic process on how to do it. So you can always come back to the slide to see the steps. So if we are given percent composition, they've done an analysis and found out it's a certain percent this, certain percent that. We're going to assume we have 100 grams of it. Therefore, we're changing all of our percents to masses. Then you're going to convert mass to moles using molar mass. So once you've done that, now you have the mole ratio. But we want whole numbers. So we're going to change the subscripts to whole numbers by dividing by the smallest number. Sometimes you're going to have to manipulate the numbers even more if you still don't have whole numbers. And usually that works by multiplying it by 2, all of the numbers by 2. And if that doesn't give you whole numbers, then 3 usually works. So we'll see one of those in our examples. So our first example problem here. An analysis of a compound determines it is 36.5% sodium, 38.1% oxygen, and 25.4% sulfur. So somebody has done a chemical analysis on an unknown compound, and that's the information that they give us. So what is the empirical formula of that compound? Well, we're going to assume we have 100 grams, change it to moles, divide by the smallest number of moles. That's going to give us our ratio. The rest of the work is just going to be math. And so we may have to do some multiplying. So let's do our first example. All right, so we have that analysis. So analysis of this, and we're going to determine our empirical formula. So the first thing we're going to do is change everything to moles, just using molar mass. All right, so when we change this to moles, we get 1.588 moles of sodium. Notice that I have 3 sig figs. I tend to keep 1 extra sig fig here just to make sure that my ratios come out correctly and I'm not making any rounding errors. So oxygen, we're going to change that to moles, and we get 2.3 0.381 moles of oxygen. And for sulfur, we change it to moles and we get 0.792. So we've found what the ratio is, but we can't write a formula like this because this says sodium 1.59, oxygen 2.38, sulfur 0.792. So we've done the work to find out what the ratio is. We have it, but we need to change it to whole numbers. So what we're going to do is look at our ratio, find the number that's the lowest number, and divide each of them by that lowest number. So this is our lowest number here. So we're going to take this one divided by the lowest number, this one divided by the lowest number, and this one divided by the lowest number. And when we do that, oh, here we go. I was trying to find my work here. When we do that, we get 2.01, 3.01, and of course 1. We choose the lowest number and then we divide everything by that because then that assures to give us one of them that's going to be a 1. It's okay to round this to a 2 and round this to a 3. As a matter of fact, here it says it's okay to round plus or minus 0.09. So we're going to round this, and then what we get, that's our ratio. So sodium 2, oxygen 3, and sulfur is just a 1. So that's going to be our empirical formula. Some of you may recognize that is actually sodium sulfite. So it should be Na2SO3, but that's okay if you didn't notice that. We're just going to write it like that to show the ratio of all the atoms in the compound, and that's perfectly fine. Okay, let's do our next example. Our next example, someone analyzes an unknown. They find it's 52.9% aluminum and 47.1% oxygen. So what's going to be our empirical formula? We're going to identify what this unknown is. So we're going to change aluminum to moles, and we get 1.961. And this is just the molar mass off the periodic table. And for the oxygen, we get 2.944. All right, so that is our ratio of aluminum to oxygen, but we want to know our ratio in whole numbers. So we are going to divide both of them by the smallest number, which is our 1.961. We get 1. And this we can divide by 1.961, and we get 1.5. Well, that's still not a ratio of whole numbers. So we're going to have to do some additional work. So we need to multiply all the numbers by 2 in order to get whole numbers. So I can see if I multiply this by 2, I get 2. If I multiply this by 2, I get 3. So then our ratio is actually 2 to 3. So our answer is Al2O3. That's going to be our empirical formula. Okay, so that's when they give you your analysis information in percent. Sometimes, instead of that, they will give you the information by providing the mass. So it'll say something like an unknown compound was analyzed and found to have this many grams of this many grams of that, et cetera, et cetera. So for this one, we're basically skipping the first step. We don't have to assume 100 grams because like up here, it was given in percent. So then we're going to assume we have 100 grams. And if we had 100 grams, that would be 52.9 grams of aluminum. So that's why we put that there. And 47.1 grams of oxygen. That's why we put that there. But on these, they're going to give us the mass. So we change it to moles. Same thing. Divide by the lowest number to get the ratio. And then manipulate the numbers if you need to. So an analysis of a 25-gram sample of a compound determines it's 11.8 grams of copper and 13.2 grams of chlorine. This number right here doesn't really mean anything to us. It's just saying that's how big the sample was. It does tell us that it's all copper, and it's all chlorine. So what is the empirical formula? So we're going to convert grams, this should say moles, convert grams to moles, divide by the smallest number. All right, so let's do that here. So we're going to convert copper to moles, and we get 0.1857 moles of copper. And then the chlorine, we get 0.3724 moles of chlorine. So after we do that, we're going to divide by the smallest number. So we're going to divide both of them by 0.1857. And this is going to give us a 1, and this is going to give us a 2. It's going to round up to 2. So therefore, our formula is going to be copper, it's just going to be 1, and then chlorine is 2. So we can get to the same answer using the mass that was given to us. Same exact process, except it's not a percent that we change to grams. We just start right with the grams. All right. So the empirical formula is the lowest whole number ratio. Many times the empirical formula and the molecular formula, or what we're going to call the actual formula of what we're talking about, are the same thing. Like when we did this example back here with copper chloride, this is copper 2 chloride, well, that's the empirical formula. That is also the molecular formula for copper 2 chloride. They're the same thing. Sometimes there's a difference. So molecular formulas are the real formula, the whole number multiple of the empirical formula. And sometimes that whole number multiple is 1. So for example, this right here, benzene, C6H6, that's the actual molecular formula of benzene. Its empirical formula is this. This is actually a molecular formula of a compound. Its empirical formula is this. Now we can calculate the actual molecular formula by being given the molar mass of the actual molecular formula, and we can do those kinds of calculations, but we are not going to do those this year. But I do want you to know what the molecular formula is. It's the actual formula, and the empirical formula is just the lowest whole number ratio for that actual formula. And that's how we do empirical formula problems.